everybody. I am so excited to be here. Thank you all for joining for our program this morning. We're going to be going over machine learning fundamentals, courtesy of free training provided by our friends at NVIDIA and the Deep Learning Institute. Training also helped to be put together by our friends at University of Oxford. So my name is Scott Glendaniel, and I'm going to be conducting our class for this morning. So who am I? Why am I here? Why am I causing you to get up at this ridiculous hour of the morning? Thank you all for joining. I've been involved in machine learning and artificial intelligence for a ridiculously long time. Matter of fact, I am going to give you all a secret confession. I am older than dirt. Okay, so I just passed my 39th anniversary in the field on March the 3rd of this year. Yes, I started in 1986 working in machine learning. I have worked as a consultant. I've worked as a trainer. I've worked as a mentor. I was a practitioner for most of those years. I won International Data Scientist of the Year a couple years ago, for whatever that's worth. I've worked for major clients you've probably heard of: Audi, Mercedes-Benz, Los Angeles Times, Bristol Myers Squibb, Coca-Cola, probably some other organizations, but none of that is really all that particularly important. What's really important is that I am here to try and help you guys to the very best of my ability. So I am going to, and yes, hey, Kadisha, good morning. Nice to see everybody here. I am going to try and walk you through the training this morning and see what I can do to help you all in terms of learning the basics of machine learning. And we're going to be doing this every week. So here we are. We are off to the races. Okay, so what are we going to be talking about this morning? All right, so the first thing we're going to be starting with is, what is artificial intelligence? And also, in addition to that, what are the types of AI? What is machine learning? And how are those two things different from one another? Because one of the things that our industry is not particularly good about is definitions. We like to call almost everything almost exactly the same thing, just to make sure that we're all thoroughly confused. As soon as we come up with one definition that makes a heck of a lot of sense, we're like, no, we're going to throw that out. We're going to call it something different. So we're going to talk about what are the differences between those two types of machine learning versus types of AI. What is an artificial neural network? Because we also like to use really fancy terms whenever we can. What is learning in a neural network? What is deep learning? What are types of layers? What are CNN architectures? And before we get too far down the path, when I refer to CNN, you'll learn very quickly, we're not talking about the news broadcasting network. We're talking about something completely different. We're also going to talk about different flavors of CNNs, RNNs, LSTMs, GRU, not Grogu, little character from Star Wars. No, that's not it. And we're also going to talk about transfer learning. So those are all the different topics that we're going to try and get into today. We're not going to have everything memorized by the end, but you should have a much better flavor by the end of this session than you did before you started. So with that, we're going. So the learning objectives look very similar to the outline that we just went through. You all can read this pretty well. Excuse me, I got a sip of coffee if you all don't mind. So I'm not going to repeat all that because we just went through it on the outline. So you'll already have a pretty good idea of what this is going to be. All right. So let's talk about how we got here and sort of the different circles that all this falls into. So in the 1950s, we came up with the first artificial intelligence concepts. These are sort of the basics that everything was built on. So if any of you happen to see a movie that came out several years ago with Benedict Cumberbatch. And what a name. How would you like to go through life as Benedict Cumberbatch? Amazing actor, but boy, that's a lot of syllables to go through life with. Called The Imitation Game. In The Imitation Game, he plays a very famous scientist named Alan Turing. And Alan Turing was most famous for leading one of the teams at Bletchley Park during World War II for trying to crack the code the Nazis were using on a machine called Enigma. And he was a pioneer. Wasn't the easiest person in the world to get along with, but a true genius. And he tried to think about what is beyond the nature of machines, but what is thinking? What is intelligence? And could we try and come up with an answer to a very simple question? Can machines think? And as he sort of thought through this process, what is thinking? What is intelligence? And could we come up with a test on how that might work? So it's like, will humans have intelligence? What would artificial intelligence be? And what would a test we could come up with look like? So that is now called the Turing test. So those are the very first sort of embryonic concepts for artificial intelligence. And that came out in the 1950s. The very first use of the term for the Turing test and artificial intelligence was 1955 at Dartmouth College. The first time that anyone saw the use of the term artificial intelligence. Very first conference on artificial intelligence was 1956. So this stuff is not exactly brand new. So we're going to be coming up on the, gee, can Scott subtract in his head, the 70th anniversary of the first conference next year. Then in the 1980s, we had digitalization and faster processors. And this was sort of the dawn of what we refer to as machine learning, which is sort of a subset. So machine learning is basically, I'm going to take a set of data, and I'm going to look in this data and say, can I find a pattern in here? So I'm going to use a set of algorithms, which are basically just procedures. You know, we like to use all these fancy terms as I was measuring. An algorithm is really just a process. It's like a recipe. So I'm going to go through and I'm going to compare all these numbers and look through and say, is there a pattern that simplifies the sort of mass of numbers? Because if I could learn the recipe, if I could apply the recipe to all these numbers, maybe I could store a pattern or a model that I could use in the future. So I could look at stuff I already know to be able to predict stuff that I don't know. And that's basically it. That's essentially what machine learning is. So then we come to the 2000s, and as we were looking at all these recipes, we came up with something called deep learning. So deep learning is a very specialized type of recipe, type of algorithm that uses something called neural network that we'll talk about in a couple minutes. But deep learning is just a flavor of machine learning. Machine learning is the subdivision of artificial intelligence. So, you know, the sort of Russian dolls they have, where one doll fits into the next doll, fits into the next doll. That's basically artificial intelligence, machine learning, deep learning. So that's probably the easiest way to understand these pieces. Do we have any questions so far? Going once. Going twice. No, too slow. All right. You can actually put questions up anytime, but I won't be able to answer all of them as we go. All right. So what do we come up with for artificial intelligence? Well, intelligence exhibited by machines programmed to sense, think, and act like humans. Now, one of the things that's really important to remember as we go through this is these definitions are not agreed upon consistently by everybody 100%. And a great way to start a bar fight with a bunch of data scientists is to have them hash out this definition and watch them go at it. But this is the definition that we're going to run with for this course. So essentially, we're trying to say, if a machine exhibited behaviors that imitated what human beings could do, that level of intelligence, hence the movie called The Imitation Game, imitating human intelligence, that's what we're going to run with. So if you think of a human being, how does a human being demonstrate intelligence? Well, we've got sensory receptors. Anybody want to type into the chat, what would a sensory receptor be for a human being? You got a bunch in your head. Hint, hint. Vision, your eyes. Hearing, your ears. So basically your senses. So those are our sensors. As opposed to a machine, what would a sensor for a machine be? Well, if you've got an autonomous vehicle, self-driving car, you might have its radar, you might have its LiDAR sitting on the top, you might have cameras, you might have some type of other type of radar, you might have a sensation for wind speed on how far it's going, you might have a GPS sensor to be able to detect its position. Those are its sensors. But for a human, it also has reasoning, we hope. It's going to have decisions and actions that it takes. AI mimics that human intelligence and behavior with sensors, processors, and mechanical parts. AI is now better than us in recognizing images, playing games, some medical diagnostics. And be careful with anything that we talk about in this class. When anything is expressed as an absolute, we're talking about genuine rules of thumb more than anything else. And autonomous vehicles some of the time. In the future, the dream is that machines will be better at sensing emotions, sense of humor, ethical decisions. The jury's still out on that last one. All right, so now we understand what intelligence is. We understand the comparison between humans versus machines. So now let's go ahead and say, all right, now we have some kind of basics. What are the types of AI that sort of get us there? All right. So pretty simple categories here. We've got weak, strong, and super. Who comes up with these names? I don't know, but we're running with it. Weak AI is what we call narrow AI. So it's how wide is the focus of these types of approaches. So in weak AI, we can only do specific tasks like a human being or better. So it's going to do one thing. It's going to do one thing pretty well and not much else. So the traditional way, there wasn't really any learning to it. Someone write down a set of rules. Anybody happen to know who was the first computer programmer? Anyone? 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 Ada Lovelace, actually a woman, who came up with a set of constructed rules for a machine that was constructed by Charles Babbage. This is back before the Civil War. It was just a mechanical device, no power source, just a mechanical machine. So there was no learning to it. You would put an input in, and she would write out a set of rules. The machine would follow that set of rules. There you go. In a modern sense, however, it would learn from experience. You would set up a situation, we were just talking about before, would learn from the experience of that set of rules. The machine is trained on that data. That's sort of weak. Narrow function, didn't do a whole lot of learning, but a little bit based on experience. Now, strong AI, the idea is that it would be equivalent to human intelligence. Can solve many types of problems, can choose the problems it wishes to solve, has self-awareness independent, no human intervention needed. Hint, we don't have this yet. And there's an argument to be made that we may not ever have it. And the reason why is people don't even agree on exactly what that would look like. And the push for this is what's called AGI, for our famous note takers out there, artificial general intelligence. This is more of a concept. This is the stuff that you see a lot in science fiction. But we haven't seen a tremendous amount of progress on this. But there are certain scientists in the field who believe this is going to happen any day now. I'm somewhat of a skeptic. I would suggest that you be a little skeptical too, because We still have a lot of problems with artificial intelligence that we're still working on now, that we're trying to work out. We still have problems with hallucinations. We still have problems with general applicability. We still have problems with coming up with a routine set of measurements on how we're going to do this. So be careful on that one. And then super AI was supposed to be superior to human beings. Now, let's talk about the edge. And no, I'm not talking about the band member from YouTube. For anyone who's old enough to remember the band member from YouTube, it comes from my era. I'm sorry, I'm old. All right, so the edge means edge computing. We're talking about, if you think about the cloud or centralized computing where everything's all together in one place, that's centralized computing. The edge means I'm going to push computing out to the very outside. So if I am working in agriculture, and let's say I've got a system that does irrigation for fields, there's one of two things I can do in terms of where I'm going to have the actual intelligence sit on whether that's irrigation is going to run for that day. I can have it all controlled within a centralized computer system, which is how most systems have run for the entire time we've had computer systems. Or I can have it at the edge. I can actually have it within the irrigation system itself. So let's say each individual, I'm going to call it a sprinkler. It's more sophisticated than that, but just to make the terms easy. I could actually have intelligence sit in each individual head of that irrigation unit, where it could make a decision based on the exact conditions it is identifying right there, right where it is. So maybe it's sitting in a situation where it's sitting in a puddle for whatever reason. For whatever reason, water is collected there. It doesn't need to fire. It doesn't need to irrigate. So it's going to make a decision and apply a rule right there for its individual application. It's not going to fire. But 3 feet away, direct sunlight is just bearing down on that guy. It knows that it needs to fire more than the other irrigation heads next to it. So it's at the edge of the system. It's going to make a decision right there. That's more of edge computing, where each individual node or element. This is really important for things like manufacturing, for things like where you have a very dispersed system, where each individual component can make a decision. This is also where you hear IoT, or Internet of Things, becomes really important to fire. So that's what the edge computing is going to be involved. So you've got telemetry, you've got sound, you've got vision. You can see all the demonstration of the different components of that are sitting there in the diagram that you see there. So that's AI at the edge. All right, so I'm going to pause again. Do we have any questions so far right now? Any questions? Feel good? Let's see. Hold on, because I'm not seeing anything yet. Okay, we're moving on. All right, so what is machine learning? We've already talked about this before. We've got the data, it's looking for a pattern. Within that data, it's going to look for something particularly called features. The features are independent variables. They are the inputs. You're also going to have a target usually. That target is going to be what I'm going to try and predict. That's the outcome. And the algorithm, what do we say the algorithm was before? Anyone? It's the recipe. It's the process that I'm going to follow. All right, now algorithm requires feedback during training and the learning phase. So it's going to go in and it's going to make an estimate by applying that recipe, and it's going to see what happens. Now, machine learning types fall into a bunch of different categories. Supervised. Now, this is a really silly name, and I wish they hadn't used this name. but I'm going to give you kind of a wacky definition that makes it easier to remember. Most of what you will be working on in your careers is going to be supervised learning. In supervised learning, I have a particular target or an outcome I'm looking for. So like in fraud detection, I'm trying to figure out, is a particular transaction fraud or is it not fraud? So that is my target. That is my outcome. The way I like to think of it is that's also my supervisor. I'm trying to figure out for a supervised outcome, is it fraud or not fraud? So that's the way I like to remember. Unsupervised is very different. Unsupervised says, I got a bunch of data here, and I'm trying to see if there's sort of pockets or groups or segments, not based on any one particular supervisor or target or outcome, but I'm just trying to see in general. So I got a group of people who came to a concert, and I'm trying to see, well, do they fall into certain categories like age groups or ethnicity or geography? Did they all just come locally or did they come from all over the world? What other types of groupings or categories did they fall into just by themselves? It's not one particular target I'm looking at. I'm just trying to come up with categorization. That's usually unsupervised. Semi-supervised falls somewhere in between. I've got some sort of categories that I'm looking for that I'm identifying and some that I'm not. Semi-supervised isn't all that common. It does happen, but it's relatively rare. The last one on the group is the one that's become really popular, reinforcement learning. This is the one that's really kind of wacky because reinforcement learning is self-driving cars is the best example. It's the one that most people turn to. For reinforcement learning, I have a problem I'm trying to figure out. So imagine that we have a toy car, not a real car, a toy car. And I'm going to put this little car in a maze. And this little toy car is going to go through the maze, and we're going to see if it can get from the start of the maze all the way to the end of the maze on its own without banging into any of the walls. So it doesn't have a data set to start out with. Remember we said for supervised learning, we got a data set. We're going to look, see if there's a pattern in there because we're going to look at the outcome. Reinforcement learning, I don't even have any data yet. So the car is going to start out and it goes 2 centimeters and bang, goes into the wall. Well, that's a problem. That didn't work out terribly well. So it's going to write down, this is what I did, this is how far I went, banged into a wall. That probably wasn't such a great idea. So it's going to write that record out. Right now I've got one record. Going to try again. Boom. Banged into another wall. No, that wasn't such a great idea either. Now I've got a second record. Don't do that. And it's going to build up this set of records over time. And what it's going to do is it's going to do this over and over and over and over again. It's building its own data set as it goes. And then it's going to learn from the patterns from the data set as it builds. So through reinforcing what worked and what didn't work, it's then going to build this body of knowledge on its own. So it's not just taking data and learning patterns, it's actually building the data as it goes. Okay, so here we go. Supervised machine learning. We've actually already kind of talked about this, but training data labeled ground truth. God, I love these expressions. Ground truth. All right, anyhow. The expected algorithm result. So we're going to go out, and this says that it's very expensive. Well, it depends. It's very expensive unless you've already done it. So, for example, let's say I've got an email campaign. And my email campaign is to go out and sell, what am I going to try and sell here? I'm going to try and sell my coffee mug. And as you can see, this is my well-loved coffee mug. You can see I've had it so long. Maybe you can't see, you know. All right. You can see I've had this so long, all the lacquer's coming off the top of it. Poor thing. I'm going to try and sound like coffee mug for an email campaign. And I know how many people I sent it to. I know whether it bounced back or not. I know if they opened the email. I know if they clicked on the link to the email. I know if they actually purchased the mug, but the mug without the missing lacquer. You know, I only sell them the good mugs. I wouldn't sell them the used stuff. All right, so that's my beta set. Cool. Well, if I've done this for a series of years, I now have a data set that I can go through. That's not expensive. Easy peasy. But that's not what we're talking about here. Here, let's say that I've got a series of photos that have just been collected. I've got all the photos that have ever been posted on Instagram, and I have no idea what they are. So I've got cats and dogs and furniture and pictures of my favorite movie stars, and I've got pictures from my garden and all these different plants that I've looked at, and I've got pictures from science experiments, and I just got all these photos. I got no idea what this stuff is. All right. So I've got all this data, and it's all unlabeled. I don't know what it is. Well, somebody's got to sit there and label all this stuff if I'm going to build a model. Because if I'm going to build a predictive model that says, yeah, this is a kitty cat, and this is a dog, but not only is this a dog, but it's this breed of dog, somebody's got to sit there and look at each photo and label that stuff. That's why it gets expensive. So that's why they're talking about ground truth can be expensive for labeled data, because it's like photographs. Somebody's got to sit there and do that. As opposed to an email campaign, I already know that data. That's not so expensive. All right. So I've got my labeled observations. And I'm going to take my labeled observations and I'm going to break it into two groups. I'm going to have a training set and I'm going to have a test set. I can't tell you how important this step is and how many people are like, yeah, too much trouble. I'm not doing that. I'm just throwing everything in there because my results are going to be great. I'm going to put every single record into my training set. My results are going to be awesome. Lots of people do it still. Don't do that. And the reason why is most algorithms in artificial intelligence and machine learning aren't that smart. What they are is fast. And they also tend to be what we call greedy. And they have a nasty tendency of memorizing the answers. So again, I've already told you I'm older than dirt. So when I went to math class a gazillion years ago, rode my dinosaur into school, we used to have these math books. And you would go through the math books. Did they even have math books anymore? I don't know. Maybe it's on computers. But we used to have actual books. Imagine that. And like every other answer, the answer, good morning, would have, the answer would be in the back of the book. So let's say the odd numbered questions would have answers in the back of the book. And the even questions wouldn't. Well, algorithms are really famous for like memorizing all the answers in the back of the book. They haven't really learned the pattern. Hi there. They haven't really learned the pattern. They just memorize the answers. So if you let your algorithm see all the training and all the test set, you don't know that they've learned the pattern. They may have just memorized the answers. This is what we call overfitting. And it's terrible, and it happens a lot. You don't want it to do that. So we're not, I'm glad it's insightful. Thank you, Peter. We want to make sure that everyone has the best chance of having the model learn the actual pattern. So we're going to hold some of the records back. And we're going to say, hey, algorithm, you don't get a chance to see these records. I'm going to test you on these at the end of this process. And I'm not going to let you see them at all because you're not going to get a chance to memorize all this stuff. That's why you hold this back, because overfitting happens all the time. Overfitting is terrible. It's a disaster. And yet some people are like, no, I'm going to learn every single pattern there is. I'm going to put all my data together. Really tempting? Really tempting. Don't do it. So that's why you have a training set. That's why you have a test set. All right. So you'll see on the training set, we've got a machine learner. That's what we're going to look for our patterns on. And the machine learner is going to come up and it's going to create a model. But we're going to test whether that model actually learned it or learned the actual patterns or not by applying it to the test set. And then we're going to evaluate those results with some statistics. All right. Everybody loosely clear on that? Labeled observations, split into two groups, hide the test set, let the algorithm only look at records from the training set, builds the model from just the training set, and then we're going to test them at the end of class against the test set. And then get the results. All good? Going once? Going twice? Sold. All right. Now, there are two types of machine learning that we're going to try and do. And I really hate these labels again. You can tell I'm not a big fan of the labels that we use, but they are what they are. One is called regression, one is called classification. This is why I hate these labels, because it shouldn't be regression and classification. Let's start with classification, because that's the one I do like. If it is a classification problem, I'm trying to assign a record to a class, a bucket, a category. So this is something that is fraud versus non-fraud. One category or the other category, that's it. You belong. Thank you, Rochelle. Hope I said that right. Or it's a car color. It's blue, it's red, it's white, whatever. Or it's a dog breed. It's a Chihuahua, or it's a Rottweiler, or it's a category. Nice, clean break. You belong to one category. All right. They call the other one regression. What that means is it's a number. So I'm going to try and predict what my house price is going to be next year. So it might be worth $50,000. It might be worth $50,025. It might be worth $49,999.99. So it's a continuous number. So think numerical. The reason why I hate the term regression is regression is an algorithm. It's not an outcome. So think numerical. Think continuous number. But in the field, we tend to call this a regression type. Everybody loosely clear on that. Now, I'm going to give you the one that screws everybody up. So if you're taking notes, now is the time. Attention, all units. Now is the time. If you've been snoring through this, I appreciate that. I'm doing the best I can. Haven't finished the full cup of coffee yet. I'm getting there. This is what's going to mess you up if you ever get quizzed on this. If you are living in a country such as the United States, where you have numbers that are categories, hang in here with me, such as in the United States, our postal codes are called zip codes. So let's say that your zip code is 21227. That's a number, right? 21227 is a number. So you're like, I remember Scott Glendaniel told me in this class that if it's a number, it's a regression. No, not exactly. Here's why it isn't. Because the way a zip code works is it's actually a category, because they have broken up a map of the United States into tiny little boxes. And you're either in the box or you're not in the box. All right. So what is a rule of thumb you can use to say, if it's a number, how can I be sure whether it falls to the regression category or it falls into the classification category. And here is your answer. So with your bright, shiny pencil or your keyboard or whatever the heck you're using, does it make sense to perform math on it? So for example, does it make sense to subtract one zip code from another? No, because it doesn't give you the distance. There's no meaning to one zip code subtracted from another. It doesn't tell you anything. It doesn't provide you any information. Math doesn't make sense. Does multiplying two zip codes one by the other make any sense? Not really, no. But I could subtract one income from another and tell the difference between two incomes. That kind of makes sense. I could subtract a person's age at one period in time versus an age another period of time and figure out how many years difference was. Well, that kind of makes sense. So if the math makes sense, it falls in the regression category. If it doesn't, it's probably regression. Does that make sense? Everybody good? Questions? Bueller? Right. Unsupervised machine learning. Bonus points if you have studied machine learning before. Can anybody tell me what they guess the second graphic with the blue, green, and red is a graphic of? Very famous data set. Anyone? Type in the chat. Think plants. You're not a real data scientist if you can't. The iris data set. That's what it comes from. Right. So we're trying to figure out what category something falls into. And in this particular spread of data that you see over on the right-hand side, you're a green dot, you're a blue dot, or you're a red dot. So those are our categories. We're trying to figure out where the barriers are for those groups. And we assign a cluster to it. So we're looking at the data to try and find out where the barriers are. So k-means clustering is one of the ones that's used here a lot. Support vector machines, used a lot. Those are good examples. Everybody still good? All right. Semi-supervised machine learning is the bane of most people's existence because everyone gets quizzed on it and it's not used all that long. But it sits, as you might guess, it sits somewhere between supervised and unsupervised machine learning. It's a hybrid model. Solves the problem of not having enough labeled data to train a fully supervised machine learning model because you need to have enough data to get there. So the training data, you take small labeled and unlabeled data set, you train the model with the labeled data. And you're like, well, records that look like this tend to be that. So I'm going to guess that because you look like these, I'm going to guess that you belong over here. This is like in case of emergency, break glass. So I'm going to give you a career tip here that you're not going to find anywhere else. At some point in your data science, AI, machine learning career, you are going to have the following thing asked of you many times. A senior muckety-muck is going to come storming into your office. I've got a big meeting, and the meeting's in 10 minutes, and it's with all these people. And I'm going to ask you to do something impossible that you don't have time for. So just do it quick and dirty. My least favorite expression of all time, which is code for break every single rule that you've been taught on how to do an analysis. But do it quick and dirty. Meaning, I didn't plan, I'm the senior muckety-muck coming to you. I didn't plan enough time for you to do this the right way. So it's my fault. But I still owe a senior or muckety-muck this result, and I need to present it in the meeting. So I'm going to make this your fault. And I'm going to convince you to break all the rules to save me from senior muckety muck by saying, just do it quick and dirty. I'm going to force you to give me an answer. I'm going to run into the meeting with senior muckety muck. I'm going to give the answer. And if it's wrong or there's a problem with it, you will be thrown under the bus. And all mention of quick and dirty will quickly fade. And it will end up being your fault. Now, there aren't a whole lot of great options in this scenario. And let me tell you a true story. When I worked in a financial services organization many years ago, my boss was stuck in this situation of trying to do a forecast with like next to no data science problem. And she said, this is a ridiculous thing you're asking me to do. I don't have enough data. The problem's not set up well. We don't have enough time. This is insane. No, you must do this. No, I'm not going to do it. You will be fired if you do not do this. So she pulls our team together. We work through the night into the next morning. I think we left like 4:30 the following morning to turn this ridiculous analysis. So she has a one-page analysis, and on top of it, she staples a full page of all the reasons why this is a ridiculous analysis, doesn't make sense, should never be used, blah, 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 blah. Thought recovered. Senior executive takes the top sheet, unstaples it from the document, and turns in the bottom sheet with flawed analysis. And the top sheet never saw light of day. True story. So be careful. So this is one of the reasons I'm not a huge fan of semi-supervised machine learning. Also why I'm not a huge fan of synthetic data, but we'll have that conversation another day. Be really careful with this stuff, folks. All right. Reinforcement machine learning. This is what we were talking about before, where we had our little toy cars in our maze trying to generate their own data. So there's no training data to start off with because it's going to generate those records as it goes. Machine is trained to make specific decisions, machine interacting with its environment, trial and error. But you give a reward system. If it gets all the way to the end of the maze, it gets X number of points. The further it gets the distance along the maze, it gets a higher number of points, et cetera and so forth as it goes through. Everybody good so far? Those are our 4 types. Questions? Looking in the chat. Not seeing questions. All right. Deep learning. This is probably going to be the hardest part that we get through. But we're going to try and simplify it. And we're going to do it like this. You're going to, first of all, can people please respond? Hold on. Let me get this to work. Can people please put some comments in? I'm actually begging for comments at this point. Can you see my cursor move on your screen? Are you seeing the cursor? Please say yes or no. Please type comment on your LinkedIn if you can see this happening. Henry, are you there? Yes. We have a yes. Yes. Thank you, sir. Appreciate it. All right. All right. See our output layer? Our output layer is what we're trying to predict. This is our objective. This is our. Thank you, Alvaro. Appreciate it. Thank you. Beautiful. At some point here, you're like, yes, I'm talking to the cat. The cat is getting a fascinating lecture about artificial neural networks. I don't know if anyone else is here. All right. Thank you. The output layer is our target. That's what we're trying to predict. The input layer is what we're starting with. So let's say our output layer is housing price. Let's say it's the famous Boston housing price data set. And our input layer might be how many bedrooms it has, what the square footage is, latitude, longitude, all the good kind of stuff. The way it works is each of the inputs has to be converted into a number. And what a neural network does is it creates combinations of those inputs in what's called a hidden layer. So it uses a mathematical set of combinations for all of the inputs. And you end up with these squiggly lines. Now, question for you, because I think I'm the oldest person here. I'm not sure. But please, someone, if anyone has heard of spirograph, type an S in the comments or type spirograph. If anyone has heard of spirograph, the kid's toy. No. All right. Never mind. Good morning. All right. So it creates all these different combinations. And then it says, based on those combinations, is it more likely to be a housing price of this or a housing price of that? Yes. Thank you, Annette. So Annette, you know what I'm talking about, where you use the swirly thing with the pen and you do the circly. Never mind. Anyhow. All right. So Annette, you and I. Yes, exactly. Thank you, Annette. Yes, painting. Yeah. No, all right. Well, Peter, you missed out. Peter, I will try and send you a picture of spirograph when we're done. You missed out. It's cool. Anyhow, it's going to say if I had a combination of this many bedrooms, this many baths, this square footage, this latitude, this longitude, etc., and so forth. If I had all this kind of stuff, what would I guess the housing price would be? All right, and then it's going to exactly gears on the pens. You do the pins, and you had to have a piece of cardboard, and it's going to say if it was really close to what the actual house price was, it's going to say you did a really good job, hidden layer. I'm going to give you more weight. Your guesstimation of how to combine all these things was really good. If, however, you came up with a really wacko combination of these inputs, you were bad. And I'm going to give you a lower weight. And it's going to run this over and over and over again and try and adjust the weights until this neural net, until the set of weights comes really close to what the optimal combination of all these variables is. This is really complicated. And it's hard to do with just one guess. So what do? We give it lots of guesses. Now, I'm not going to go through all this right now. Because, oh, bless you, Annette. Thank you. All right. So you don't have to learn all this right now. If anyone is dying for a deep mathematical representation of this, go to 3 blue, 1 brown, or I will actually, for next time, I will get you an excellent video of this. Me trying to do this with hand waves right now is not going to help you all that much, but in essence, it's a consistent set of trying to balance these weights to predict our outcome. And if it doesn't get it right with one hidden layer, it adds more layers and more layers and more layers. But not all layers are created equally. No, I say no, they are not. So they came up with different kinds of layers on how to adjust these combinations. All right, so one of the classic examples of this was how to guess what a handwritten digit really meant, because handwriting is a mess, especially mine. So in this diagram over here, if you can, I hope you can still see my cursor. It looks like it's showing up. All right, so A, this is somebody's handwritten version of the letter A. This is actually pretty good. It kind of looks like an A. And then what a computer does is it converts this into a 2D set of pixels, and it says which pixel fired to make it look like an A. It says, all right, so it converts this, and it says, all right, well, this first box over here, yeah, nothing there, so I'm going to give it a 0. The second box, yeah, nothing there either, give that a 0. Third box up, we got something here. Black, give it a 1. Next box, yep, something there too. Black, give it a 1. Nothing in the next, give it a 0. All right, so this is really painstaking. I'm not going to read all the boxes. So it takes this whole mess and converts it into a matrix, numerical. Each pixel has a numerical value. The computer doesn't actually see anything. It gets a matrix of numbers. It says, all right, I got a matrix of numbers. Well, the A is a really simple example. But what happens if it has something a little more complicated, like a number that also has grayscale in it? Right? So it's not all on or off. But if you see in here in our 8, it's not just black or white. There's also some gray because it's not fully marked in. There's sort of levels of gray. So now we've got to adjust that to say it's not fully black, it's not fully white. And then you get this wacky looking matrix over here on the end of our 8. It's going to convert that. But wait, there's more if you call now. What if you have a color picture? What is it going to do now? Well, now it really gets really complicated. RGB is our color scheme for red, green, and blue. By the way, trivia for you. If you have ever looked at a newspaper really closely, you know what a jeweler's loupe is, one of those magnifying lenses? Look at it really closely. There are only 4 colors in a newspaper picture. And it's not exactly this, but it's close to it. What are the 4 colors in a newspaper picture? Or in a piece of direct mail? Only 4 colors. What are they? Anyone still awake? That was, she even found spirograph. What are the 4 colors? Black, cyan, magenta, and yellow. Those are only 4 colors. And by putting the pixels really close together, it creates all the other colors in the rainbow. So the computer is going to do a similar version to pull those backwards. And it breaks it out into red, green, and blue. And then it also looks at saturation and hue. So you can guess that if it's got a color picture, it's got a heck of a lot of numbers it's fooling with. And this array of numbers gets huge. Red, yes. Blue, cyan. Yellow's right. All right. Going to convert all these to numbers so you can imagine the matrix gets enormous. So you get a fully connected input layer. Oh, Paul, I'm going to make you stay after class. All right. So if you can see just for 28 by 28, 784 pixels, this thing gets really big. Can you all see this? This is just for grayscale. And for a fully connected input layer, you can see the numbers in here get really large. Explosion of parameters and spatial information gets lost. So this isn't the world's greatest way to represent information. So you have to come up with a different way to represent information if you're going to do a neural network with computer vision. So the way you do this is called convolution, which is really a shame that they call it convolution, because I don't know if you've ever heard someone use the expression, it was a really convoluted explanation, which makes it sound like it was really confusion. But so when you hear convoluted or a convolutional neural network, it doesn't mean confusing. Okay, so convolution means something very different here. So again, pull out that pen or computing device or whatever. This means something very different here. How do you preserve all the information but shrink it down so a neural network can work with this? And I'm going to make it simple for everybody. You take a small patch of the image and you shrink it down. So you've heard of compression of images. This is basically what it's doing. So it's going to take that matrix and shrink it down using parameters like this. So the important thing to remember, the key feature, the one to write down, is that convolution is a method of compressing the information to a smaller matrix that a computer can use, so that you don't melt the computer trying to work with very large matrices. Everybody good? So think compression. So convolution is a measure of similarity between the original image and the mapped image. And what it uses is something called a feature map, because remember, our inputs are called features. Remember that? Inputs, features. It's going to create a map. All good? Hearing no complaints? And here are our feature maps. Non-linearity. This is where my brain starts to melt, but hang in there with me. Okay. If you took statistics at the college level and worked with logistic regression, type yes in the comments, please. Yes in the comments if you worked with logistic regression at the college level. While we do that, what you're going to see on this chart is a set of transformations for inputs. And basically what it does is it takes a set of features and converts it to a range. The three examples on the bottom, left-hand side, called a sigmoid, tanh, or ReLU. Elvira did. Paul did. There you go. Paul, that's exactly right. Here's the important thing to remember here, guys. Don't get lost in the math. If you have a core understanding of the math, and if you want to go deep in the math, that is fantastic. This is what I don't want you to do. I don't want you to look at the formulas and go, oh, I don't understand the formulas. I'm out of here. I can't learn this class. Nope. No NVIDIA for me. No machine learning for me. I'm out of here. Don't do that. Get the concept down. Don't memorize the formulas if it makes your brain melt. All these activation functions are doing is making it easier to convert a map. That's it. Now, it's a math function to make the map easier. So it's like a math map. For a lot of these functions, there's something called a rectified linear unit. That funky little guy down here. There's also a lot of argument over this, whether ReLU is still the best function or not. And depending on which unit you use and which type of hidden layer you use a different function. Memorizing the formulas for this isn't going to help all that much. What's important is to understand that they're different functions for different types of neural networks. That's it. If you need to look them up, go look them up. All we're trying to do here is to say there are different types of neural networks, there are different types of functions. That's it. All good? Everybody still with me? Sweet. Pooling, reducing the size of the feature stack by downsampling spatial resolution of each feature map. Okay. You'll notice a pattern from all of this. All of the sections we're going through are different techniques to reduce the volume of the data into smaller sections so that it processes faster. Pooling is a different approach that takes the matrix that you see over here on the left and converts it into something much smaller on the right. So you'll notice this is 7 times 7 is 49. So it takes this 49 matrix and converts it down to 16. Because what it's doing is it's taking a subsample and saying, what is the biggest difference in my picture? And I'm going to memorize the biggest differences in my pictures, and I just take the biggest differences, and that's what I'm going to use in my analysis, and that's going to do me just fine. But wait, there's more. If you call now, we could stack all of these techniques together. We could use a convolution, then we could use a ReLU, then we could use pooling. Why not? Let's go crazy. Let's use deep stacking. With your convolutional layers, you can take advantage of all these different techniques and combine them in lots of different ways so that I can look at my problem in all these different ways and take advantage. So imagine, I'm going to go back to my poor little coffee mug again. And instead of just looking at one picture here, imagine I had this amazing camera that could look at it from all these different ways and approaches and different types of data. And I had 3D cameras, and I had X-rays that I could look at it, and I had thermal imaging, and I could look at this all types of different perspectives. That's what deep stacking allows you to do. You don't have to memorize all this. What we're saying here is, if you're really clever, you can apply all these different techniques and get the absolute best approach by combining everything together. That's what we're saying here. And when you have fully connected layers, they learn nonlinear combinations of high-level features outputted by the convolutional layers. Features are assigned, and that should be assigned to be ED, weights which describe their contribution to recognize a particular object. And so you end up with saying, you know what? I'm pretty sure it's a beagle. I'm 92% sure it's a beagle. Hi, Eduardo. Yes, Paul, exactly right. And I'm actually going to pick up on Paul's point, because Paul, that is really important. At the end of the day, we are here to solve problems. If you're working for an organization, let's say we are surgeons. We're trying to save somebody's life, or heal the sick, or prevent disease, or something like that. If we are in e-commerce, we're trying to maximize profit. If we are in law enforcement, we're trying to make sure that we catch the bad guys and we don't catch the innocent. Also important. We are here to solve problems. That is your objective. Don't get stuck in the ivory tower. Artificial intelligence, machine learning, all these are tools to get to an objective. That is what we're here to do. Don't get so wrapped up in the tools that you stop solving the problem. If you have all these formulas memorized and you haven't helped your organization, you have failed. I have worked with so many brilliant people who are so much smarter than me. I appreciate them so much, and they can't solve a problem to save their lives. It's really sad. You need to have a balance. You need to understand this enough to make sure that your organizational objectives are achieved. That's what we're trying to get you to. The more depth you learn about this, the better you will be. The more you understand the math, the better you will be. The more you understand the definitions, the better you will be. But Voltaire once wrote, "Don't let the perfect become the enemy of the good." It's a really important lesson. Everybody good with that? If you agree, type agree. Everyone else is saying, can I please go to the restroom now? Because I'm really tired of listening to Scott talk. All right, so I think that is enough for one session. And I'm going to pick up the rest of this next week.